For decades, predicting the weather has been one of science's biggest challenges, hasn't it? Really humbling.
Absolutely.
We've built supercomputers, launched satellites, done all this stuff, and yet there's still that nagging uncertainty about tomorrow's forecast, or even just the next hour's rain.
Always that question mark.
But what if a new approach, a pretty radical one, powered by artificial intelligence, could fundamentally change the game, give us unprecedented clarity, maybe?
That's the promise.
So today we're diving into how AI is doing exactly that, how it's transforming our ability to see what's coming, from like the next sudden shower all the way to long-term climate shifts.
It's a huge area.
Yeah, and you shared some fantastic sources with us on this. Our goal for this deep dive is really to pull out the biggest takeaways. It's such a data-rich field, but also, famously unpredictable.
It is. And it's a truly fascinating shift we're seeing. Traditionally, forecasters have relied so heavily on these massive physics-based simulations, numerical weather prediction models, MWP.
Right, the big complex ones.
Exactly, incredibly complex, demanding just immense computational power. Huge machines. But AI, it offers a fundamentally different way in.
How so?
It can analyze those same vast data sets, but often in just a fraction of the time. It learns from historical trends, patterns in the past data, and often delivers forecasts that are, well, both faster and more accurate.
Okay, all right, let's talk about the specific AI tools then, the ones making waves in weather. For listeners who might already know a bit about the broader AI landscape, can you sort of pinpoint how these specific branches are uniquely suited to, well, the chaos of atmospheric data?
Absolutely. Yeah, maybe think of it less about, the textbook definition of AI generally and more about what it does specifically for weather prediction.
Okay.
So artificial intelligence at its core is just about computer systems doing tasks that normally need human smarts, like problem solving or pattern recognition. Within that, you've got machine learning, ML. That's what enables computers to learn patterns directly from data without someone having to explicitly program every single rule. They figure it out themselves, essentially.
Okay, learning from experience, sort of.
Exactly. And then a really powerful subset of ML is deep learning. This uses these layered structures called neural networks to process incredibly complex, really nuanced information. A bit like how our brains handle complex input.
That distinction definitely helps. So how are these specific technologies, ML and deep learning, being applied to the unique challenge of predicting the weather? Seems like such a messy problem.
It is messy, and that's why you see quite a diverse range of techniques. For many really crucial forecasting needs, you'll see machine learning models, things like linear regression, decision trees, random forests, gradient boosting machines.
Okay, the more established ML tools.
Right. They're incredibly effective for predicting specific variables like temperature, rainfall amounts, or maybe the probability of extreme weather happening. They really excel at finding those hidden sort of not linear patterns in massive historical data sets. The kinds of patterns that might influence, say, a sudden temperature drop or why a thunderstorm pops up just here and not over there.
And then the deep learning models, that sounds like where the really intricate, maybe more complex stuff comes in.
That's exactly right. Deep learning models handle the truly sophisticated tasks, especially when you're dealing with the sheer visual complexity of weather data.
Like satellite images.
Precisely. Take convolutional neural networks, CNNs. They're indispensable for interpreting satellite imagery. You can imagine them as these highly trained pattern recognizers. They can instantly spot the subtle swirls, indicating a developing storm, or the different textures of cloud types, stuff that would take a human eye ages to sift through, especially across terabytes of images. Then you have recurrent neural networks, or RNNs, especially a type called LSTM models. These are perfect for analyzing time series weather data.
So data that changes over time.
Exactly. Things like atmospheric pressure changes, wind speeds hour by hour, temperature trends. RNNs are designed to remember previous data points in a sequence, which is absolutely crucial for predicting how atmospheric conditions are likely to evolve.
Makes sense. Things build on what came before.
Right. And then most recently, you have things like transformers. You might have heard of them in language models, but they're also really powerful for weather. Google's MetNet-3 is an example.
MetNet-3, okay.
Yeah, these are proving incredibly powerful for longer range forecasting. They can offer really high resolution predictions because they're very efficient at modeling dependencies across both space and time simultaneously.
That's a huge leap, understanding all of those connections. Now, I also saw something mentioned about hybrid models. It sounds like maybe we're not just throwing out all the decades of traditional science.
Oh, absolutely not. That's a really important point. Some of the most promising approaches right now actually combine AI with those traditional physics-based systems.
Ah, okay. Best of both worlds.
Kind of. A great example is the European Center for Medium-Range Weather Forecasts, ECMWF. They're actively integrating AI components directly into their well-established traditional models.
Interesting. Why do that?
Well, it lets them speed up certain really complex parts of the simulations, but without compromise the underlying scientific rigor, that deep understanding of atmospheric physics they've built up over decades. It's a fantastic synergy, really, using AI speed and pattern recognition alongside the physics.
Okay, so here's where it gets really interesting for me. Where exactly is AI making a tangible impact right now, like across the whole spectrum of meteorology? Can you give us some specific applications where it's already out there being used?
Oh, it's becoming truly pervasive. And the impact is, well, pretty profound already. For short-term forecasting, what meteorologists often call nowcasting, like predicting the next hour or two.
Right, like, is it going to rain on my picnic?
Exactly that kind of thing. AI can predict rain, thunderstorms, hail, often in real time with incredible localization. And this isn't just about slightly faster forecasts. It means a city might issue a flash flood warning based on data coming in right now, just as the intense rain starts, instead of, say, half an hour later when streets are already flooding.
That's a big difference, moving from reactive to proactive.
Fundamentally different, yeah.
Yeah.
It changes how we manage immediate threats. Then thinking longer term.
Like climate modeling.
Exactly. AI is being explored heavily for climate modeling, helping with those huge, complex projections related to global warming, sea level rise, shifting weather patterns. AI can potentially improve the resolution of these models and help analyze different future scenarios with more nuance. These are incredibly complex calculations.
And I have to imagine it's absolutely critical for predicting extreme weather events. Hurricanes, floods.
Oh, absolutely crucial. AI is playing a vital role there, forecasting hurricanes, tracking floods, even predicting wildfire behavior. A really standout example is IBM's system called GRAF, Global High Resolution Atmospheric Forecasting.
GRAF. Okay.
Yeah, it uses AI to provide hyperlocal predictions down to a few kilometers, and crucially, they're updated hourly,
Hourly.
which is just a game changer for emergency preparedness, disaster response. When every minute counts, getting that fresh, localized information is vital.
I can see that.
And beyond just weather warnings, think about agriculture and disaster management.
Mhm.
AI helps predict things like droughts or even pest outbreaks by analyzing soil moisture from sensors, temperature patterns, satellite imagery.
So farmers get a heads up.
Exactly.
Oh.
Or predicting crop yield impacts. It enables that proactive early action that can, save entire harvests or help manage water resources more effectively.
That's a really comprehensive list of applications. So, stepping back a bit, what are the core advantages? Why are these AI systems proving to be such a powerful alternative or maybe a complement to the methods we've used for so long?
Well, the number one advantage, honestly, is mind-boggling speed.
Right. You mentioned that.
Yeah. While a traditional forecast might take hours to compute on those massive supercomputers, AI can often generate similar, or sometimes even better, results in literally seconds or minutes.
Seconds. That's incredible.
It is, and that real-time responsiveness is just absolutely vital during rapidly evolving emergencies, like severe storms.
Makes sense. What else? Accuracy.
Definitely accuracy.
Yeah.
AI can deliver highly localized and incredibly precise predictions. It often outperforms traditional models, especially when it comes to tricky things like the exact timing and location of precipitation. Is it going to rain at 3 p.m. or 4 p.m.? And will be over my house or the next town over?
The details that actually matter to people.
Exactly. That level of detail really enhances planning for, well, everything. Infrastructure resilience, transportation routing, farming schedules.
And I think I heard you mention cost effectiveness too. That kind of surprised me. Cutting edge tech usually sounds expensive.
It's true. Cost effectiveness is another key advantage, maybe counterintuitively. Once an AI model is trained, and the training can be computationally expensive, we should note running the forecast, the inference part, typically requires much less operational infrastructure compared to traditional systems.
So you don't need the giant supercomputer running constantly for every forecast.
Pretty much. You don't need those massive, incredibly expensive, high-performance computing facilities running full tilt all the time just to get the daily forecast out. That saves a lot of energy and money.
Okay.
And finally, I'd say AI's capacity for big data handling is just unmatched.
Right, pulling it all together.
Exactly. It can seamlessly integrate just incredibly diverse data sources, everything from satellite imagery, weather balloons, ground-based IoT sensors, radar systems, you name it. And it can quickly extract the important signals, the actionable insights from that absolute deluge of information, something a human forecaster or even older systems simply couldn't process at that scale and speed.
That really clarifies how all the pieces fit together, the speed, the detail, the data handling. Can you give us maybe one or two more concrete examples? Real-world AI systems that are already out there proving these points.
Certainly. We mentioned Google's MetNet 3 before. That's a prime example. It delivers 12-hour forecasts, updated very frequently, at an impressive 1-kilometer resolution across the U.S. and parts of Europe.
Hmm.
And studies have shown it often outperforms leading traditional models in both accuracy and, of course, speed.
Okay, so that's a big one.
Yeah. Then there's IBM's, the weather company. They provide AI-driven hyperlocal forecasts that are used by a huge range of clients. Airlines use them for flight planning, farmers for planting and harvesting, energy companies, emergency services. Their systems are designed to integrate multiple data streams constantly and adapt really rapidly to changing conditions on the ground.
So it's already deeply embedded in critical industries.
Absolutely. And one more, maybe internationally in China. Their Finyan satellites are now equipped with AI systems right on board or process the data very quickly for real-time typhoon tracking and classification. This allows for much quicker government warnings and responses in their very densely populated coastal regions. The impact of these systems is not theoretical. It's happening now and affecting daily life and critical decisions.
Okay, so given all these incredible advancements, these real-world successes, what's the flip side? There must be challenges still. It can't be all, perfectly predicted rainbows just yet.
No, definitely not. You're right, there are significant challenges still. I'd say foremost among them is data quality.
Garbage in, garbage out.
Exactly the principle. AI models are only ever as good as the data they're trained on. If you have biased or incomplete data sets, think about, say, gaps in radar coverage over oceans or remote rural areas that can lead to poor or unreliable predictions in those specific regions.
Okay, that makes sense. You need good sensors everywhere.
You do. Then there's the notorious black box problem.
Yes, the explainability issue.
Precisely. AI models, especially these complex deep neural networks, they often produce remarkably accurate results, but without really being able to explain how they arrived at that specific prediction. Why is it predicting heavy rain here? The model might not give you a clear physics-based reason.
And that's a problem.
It can be a big problem in critical scenarios. Human forecasters need to understand why the model is predicting something, especially if it's extreme weather, so they can trust it and communicate that risk effectively. Lives could be on the line. You need confidence in the forecast's reasoning, not just the outcome.
Right, you can't just say, the computer said so.
Not ideal, no. And another point, we mentioned cost effectiveness for running forecasts.
Fixed training.
Exactly. The hardware for training these massive models is still immense. While AI reduces the need for supercomputers for the inference part making the actual predictions, it still requires incredibly powerful hardware, like banks of GPUs or specialized chips like TPUs, for that initial, very demanding training phase. That's a barrier.
Okay, so data, explainability, training hardware. Any ethical concerns creeping into?
Yes, definitely. There are discussions around potential over-reliance on AI, maybe de-skilling human forecasters over time. There are concerns about potential job displacement for meteorologists, although many see AI as an enhancement tool, not a replacement. And also questions about the privatization of weather data and forecasting, which has historically often been a public service. Who owns the best models? Who gets access?
Important questions. So looking past these hurdles, what does the future hold? Where is AI in meteorology headed next?
Oh, the future looks incredibly exciting, despite the challenges. We're starting to see research into really cutting-edge areas like quantum machine learning.
Quantum, wow.
Yeah, it holds the potential, theoretically at least, for breakthroughs in solving those incredibly complex atmospheric equations far faster and more efficiently than even today's best classical computers. It's still early days, but very intriguing.
What else? More data collection.
Definitely. Researchers are developing AI-powered autonomous drones and sensors. Imagine swarms of small drones flying into hurricanes or over remote oceans, collecting real-time atmospheric data where it's currently sparse or dangerous to get.
Wow, that would fill those data gaps.
Exactly. It would significantly improve model accuracy and data diversity, feeding even richer, more immediate information into our forecasting systems.
And is there international cooperation on this? It seems like a global challenge.
There is, and that's crucial. You see global initiatives emerging, like the UN's AI for Good programs, including things focused on climate and weather. They aim to foster international collaboration, sharing best practices, and importantly, trying to make these advanced AI weather tools accessible to developing nations too. It's about ensuring equity, making sure the benefits of better forecasts are shared globally, not just concentrated in wealthy countries.
This whole deep dive has really shown, I mean, AI is truly transforming meteorology, isn't it? It's boosting speed, accuracy, accessibility, and opening up entirely new possibilities for critical climate research and disaster response. It's almost hard to wrap your head around the scale of data involved, like trying to drink from a fire hose for a traditional meteorologist, maybe, but AI just seems to, I don't know, sip it all up effortlessly.
That's a good way to put it. And I think the crucial point to keep coming back to, the real takeaway maybe, is that AI isn't here to replace human expertise or traditional atmospheric science. It's much more accurate to see it as an incredibly powerful collaborator.
Augmenting human skills.
Precisely. Enhancing our capabilities in ways we couldn't before. But, this does raise a really important question, something maybe for you, the listener, to consider further.
Okay.
As AI becomes even more sophisticated, more deeply integrated into forecasting and therefore into our daily lives, how do we navigate those challenges we talked about? How do we ensure continued investment in making AI explainable, not just accurate? How do we address the ethical concerns? And maybe most importantly, how do we guarantee that the immense benefits of this technology, better warnings, safer communities, remain fundamentally a public good, accessible and beneficial to everyone?
That's a critical point.
It really is.
Yeah.
Because this synergy, that collaboration between AI and meteorology,
Yeah.
it's going to be absolutely vital, I think, to building a safer, more resilient world, especially as we face growing climate uncertainty in the years ahead.